What I want to look at here is something called torque, and it's something we really don't look at in level 1, so it should be new for most of you. You probably know that it's related to some sort of turning motion, and it is. And so this is when we get into our rotational stuff. We've looked at circular. Torque is like force, but it's in a rotational situation. So let's try and give some examples. If we've got an object, usually it's got to be fixed. So maybe I've just got a bank and I've got a bit of wood stretching out there. Now it would pivot, and you all know it would fall because it's pivoting at that point, right? Now what's actually happening is that the mass of the wood, this is just a plank sitting on a wall, has got a mass, and we could say the center of mass is there. So for all intents and purposes, its weight force pushes down at that point there. Now what happens when you apply a force about a pivot point? What you're actually applying is a torque. So a torque, I'll use that symbol for the torque, is equal to a force, in this case mg, times a distance to the pivot point, which in this case is this distance here. And so the torque is measured in newtons meters. Now the thing about a torque is that, like forces, you can have an equilibrium of torques. So equilibrium of torques, if there's no net torque, then there's going to be no rotational motion. Implies no rotational motion. Just like a force produces an acceleration, a torque produces an angular acceleration. I'll call it alpha, an angular acceleration. And of course that's the whole object rotating, right? And that's what would happen in this case. To stop that from happening, I would need an equal and opposite torque. And since the only place I could apply an equal and opposite torque in this situation, the torque would have to be up. I mean, obviously, if I put a bit of string here, right, and pulled up, then if that string, Ft, and the string would create an equal and opposite force, times that distance is an equal and opposite torque. Torques have a direction, a rotation. This torque from mg is producing a clockwise torque. So mg gives a clockwise torque, whereas Ft would rotate it that way, gives an anti-clockwise torque. And so when your anti-clockwise torques equal your clockwise torques, you've got equilibrium of torques, and that means you've got no net torque, and that means you will get no angular acceleration. So this is torque, and we use it in a variety of situations. A common one that we have, let's just have a look. It's not a very good bar, is it? Just straighten that up a bit. A bar hanging by a string, right? Now if I could break this into two pieces, this piece and this piece, each one has its own mass, center of mass. This one produces, so that one would have a little mg, that one would have an mg. I'm taking the mass of the bar. And this one is applied at this distance, this one is applied at this distance. The one with the bigger torque, so this one's going to apply a clockwise torque, this one will apply an anti-clockwise torque. The distance being, so this one, we'll call it mass 1. Maybe we could put a mass on there, and we'll make it 4 kgs. Mass 1 equals 4 kgs. We'll put a mass there, and we'll call it mass 2, and we'll call it 6 kgs. We'll call this distance 0.2, and we'll call this distance 0.4. So the clockwise torques are equal to mass 1 times 0.2. And the anti-clockwise torques are just going to be equal to the 6 times 0.4. So the anti-clockwise torques are going to win, and you would subtract your clockwise torque from your anti-clockwise torque, end up with a net anti-clockwise torque. So the whole thing is going to rotate that way. So no equilibrium with that example. So that's it with torques. What I will do is the next video I'll do, we'll do an example where we work everything out with not just torques but linear forces.